Hello class, this is Mr. Carlson. I'm making a recording for going through Chapter 2 of Introduction to Statistics because we won't be having class on Friday. So I encourage you to maybe open up the PowerPoint presentation yourself and you can follow along as we go. Also, you want to make sure that you have the notes open, and so make sure you're looking through these notes as we go as well. We will be doing a couple examples. My intention is to make two videos. This first video is to go through the PowerPoint presentation, and then I will make a second video of doing some of the homework problems, because some of the homework problems are a little bit annoying, but I'm going to show you how to do them. So without further ado, let's go ahead and start Chapter 2. In the first chapter, we talked about the different types of data and the different types of samples. And we talked about the importance of a random sample and how that's and the importance of a simple random sample and the difficulty in achieving that and how it can introduce bias into our results. So chapter 1 was kind of the methodology chapter of how do you put your sample together, how do you actually conduct a survey. In chapter 2, we're going to look at how to display data and how to the various ways that you can show data to people. Some ways are better than other ways, and my hope is that some of this might be review, because some of this you should have seen before. So let's get started. As we know, and as you should memorize, a parameter measures an aspect of a population. The parameter is what you get paid to try to figure out, like the average age of every American, or how much income are people earning, or whatever your science experiment is. So the population parameter is that mysterious variable that we don't know. Importantly, every member of the population probably has a different value for that parameter, which makes this all the more tricky. So when we take a sample, we want to examine the data, that is, the values for that parameter. And so, as we said in Chapter 1, if you have a truly random sample, then you can get pretty accurate results of your population parameter. And so the difficulty is in getting that random sample. Now, in general, there are two statistics that we care about. And what you can see right here is what's called a bell curve. And we're going to talk a lot about the bell curve. So here is how data might be distributed. You might have most people, like for example, let's say that this is the age of everybody in the United States, for example. And so you might have a couple young people, most people in the middle, and a couple old people. And so these are called tails, and this part in the middle where the bulge is called the body. And this is maybe one of the most important distributions, and we'll talk about it a lot. Now, as we study data, whether it's a bell curve or a different type of distribution, there's generally two statistics that we care about. The first type of statistic is called the central tendency. And you can think just about the word center, right? Center, central. This is what is the value that's kind of in the middle. And so if we have data and we have everybody having a different value, what value is in the middle of everybody? That's important. The second statistic that we care about is called dispersion, and that is how spread out is your data. Is your data really centralized with everybody having a really similar value, or is your data really spread out? And so we have different statistics that measure both of these, and we'll look at those in this chapter and in the next chapter. So do members of the population have large differences, or are people consistent? So the statistics that measure the center of the distribution, the statistics that measure the central tendency, hopefully you've heard of some of these: the mean, also known as the average, the mode, the median, and the mid-range. So we're going to look at how to calculate all of those in Chapter 3. In this class, the mean is arguably the most used central tendency statistic, and so we're going to spend a lot of time calculating the mean and using the mean. And the reason we call it the mean is because there's different types of averages. So the arithmetic average is the mean. There's also the harmonic average and some other averages, so we're just going to call it the mean. But when you see mean, just think average. And there's a couple statistics that measure the dispersion of data. And so those are called the range, the variance, and the standard deviation. And the standard deviation is probably the most important dispersion statistic that we're going to look at. And I would actually argue that the standard deviation is the most important statistic in all of statistics. And we're going to spend a lot of time studying standard deviation. In fact, one of my economics professors had an interesting thought, which was that you can tell how good a statistics class is going to be, or a statistics textbook, how good it is, based on how soon they introduce the standard deviation. And the sooner they introduce it, the better, because of its importance. And so we're already talking about it. We're already talking about it in the second chapter, so that's a good thing. Let's take a closer look at this image, if I can. So here, this gives you an idea of how standard deviation measures the dispersion. So you can see this blue right here. Do you see how all of the values are very clumped together? And so this middle section is really overrepresented. So that has a standard deviation of 0.5. If we increase the standard deviation to 1, that's this red curve, and you can see that the tails are a little bit bigger and the middle peak is a little lower. And so this represents data that's more spread out. And here in the green curve, the third example, you see that the standard deviation is equal to 2, and you can see how that really flattens the curve. It really flattens the representation, and so there's a lot of people up high, some people in the middle, and more people down low. And so the higher the standard deviation, the more spread out your data is. And as a teacher, what you want is you want a high average, obviously, because you want students to do well, but you also want to be careful to have a low standard deviation, because if you have some students that are doing really well and some students that are doing really poorly, that's a bad sign, and you need to try to figure out why that's happening. Okay, so let's look at some other ideas. An outlier is a value that is far above or far below the majority of our other values. And it's a little subjective how you define an outlier. We will, by the way, before I forget, we will look at how to calculate standard deviation just like the other statistics, and we're also going to talk a lot more about why it's so important. All right, so an outlier is a value that's far above or far below the other values. In Chapter 3, we will learn a formal way to declare something as an outlier or not. And outliers are really important because they can mess up your statistics. And sometimes it's questionable if there's a really bad outlier that's really affecting the majority of your population. It gets a little questionable about whether or not you should include that in your sample or not. And so we'll talk about that more later. Maybe you want to include it in your sample and do the statistics twice, once with that outlier and once without the outlier. And so that way, but you show the data both times, and so people can see how that outlier affects the rest of the data. And we will be looking a lot at time. Any change in a characteristic over time, we can measure that with statistics as well. So we've learned the key concept that I want you to come away with is these are the two statistics that we are going to care about a lot in this class, central tendency and dispersion, and we're going to learn lots of ways to measure those. And as we do that, we're going to need to represent our data, and so let's look at some ways that we can represent our data. So this is a stem plot, and it's one way to represent data. I like stem plots because you can kind of see the bell curve, or whatever your distribution is. You can kind of see it. This is a visual way of looking at your data. So the way it works is each of these are values. So in this data, we have, it looks like the price of various objects in a store, perhaps. And so the way it works is this first digit right here to the left of the line, that represents the tens place. And the values over to the right represents the ones place. So every single number represents a member of the population. So for example, in this group, we have the number 72, we have 73, 76, 77, and 79. So that represents 5 objects in the store that have a price of $72, $73, $76, $77, and $79. And so one thing I want you to point out is we can have repeated numbers. And so here you can see that there are 2 objects in the store that are both $89, and that's why we have 2 repeated 9s. Also notice that when you're making your stem plot, the numbers should go from smallest to biggest. And so here you can see 61, 61, 62, and then we have 5 objects that were priced at $65. What do you think the price is of this one right here? We have a 15 and a 0. Hopefully you thought $150. And notice that there's a big distance between this object and the bulk of our data, and so I think it would be fair to call this value an outlier. Maybe there's one really expensive object in the store. So that's called a stem plot. And so in our notes, we have an example. Let's make our own stem plot. How can we do that? And so on the notes, we're now right here. I believe the data should match this example right here. So how can we make a stem plot of this data? So what I'm going to do is I'm just going to copy this. And this will be a little bit rough, so you'll just have to bear with me. So there's our data. And so let's make a stem plot of our data. So we're going to start by just drawing a vertical line. And let's look at the tens place. We want to go in order. So I have 5, 7, 6, 9, 8. Oh, there's a 4. So let's start with 4. So I'm going to do this. So it looks like our first digit is 4. And you should be doing this in your notes as you do this, as I do this on the screen. So we have 4, and then 5, and then 6, and then 7, and then 8, and then 9. And I don't believe we have any values of 100, so I think it stops at 9. Okay, so now that we've done that, that represents 40, 50, 60, 70, 80, and 90. And so let's put in the data. And what I recommend you do is you scratch off the data as we go. So there's 44. So we just put in our 44 right there. Oops. So now that we've done that, I'm not going to click out of the text box because then Paint will not make me be able to edit it anymore. So you could scratch off 44 because we've done it. All right, now let's look at the 5s. We have 56, another 56. And that's it. So we'll represent that with 2 6s. There's 56 and 56. Let's look at the 6s. We have 62, 63. I think that's it. So it would be wrong to do this. The homework will say that you're incorrect if you do it like that. We need to do the smaller digit first and then the larger digit. Go to the 7s. Let's see, 70, 72, 76, 77, 75, 70, 73. Wow. So I think 70, 72, and 73. Okay, then I think we have 75 and 77. Did I get them all? 70, 72, 73, 75. Oops, I missed 76. Okay. All right, I think I got them all. Hopefully I didn't miss any. I'll count them at the end to see. All right, so 80. We have 80 right there. 84 and 85. For the 9s, 93, 94, 99. And so there's your stem plot. So let's count to make sure I got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So I missed one. Which one did I miss? I know you're probably all yelling at the screen right now. One, 2, 3, 4, 5, 6, 7. I'm missing a 7. 70, 72. Oh, we have 2 70s. So there's the one I'm missing. All right, there we go. Now we have all of them. And so notice if you are missing one on the homework, just count the number of values, count the number in your stem plot, and then you will be able to get the correct answer. So that's how you create a stem plot. As you can see, this is kind of like a bell curve. We've got a lot in the middle, and we certainly have a nice tail over here on the left. I'll explain what left and right means in a minute. So there you go. I believe now we are moving on to a second example. So you can also do a two-sided stem plot. So maybe you have a characteristic that you're dividing people with, so like male and female, for example. By the way, what would that be called? Do you remember the type of data survey that is if you've broken people up into a group based on a characteristic? Do you remember? You should know this. I'll give you a hint. It starts with an S. Stratified sample. If you have a stratified sample, you've divided it between, it feels like Blue's Clues, where I just ask a question, pause for a minute, and then tell you the answer. Anyway, let's grab this data, and I'll show you how to make a two-sided stem plot. Entertain yourselves while I grab this data. All right, I'm going to do it this way. We'll do it this way. All right, that was very exciting. Okay, let's make a stem plot with this data. So with a two-sided stem plot, what we're going to do is we're going to have two lines like this. And on one side, we put part of the data, and on the other side, we put the other part of the data. And so the right side of the stem plot is exactly the same as before. So let's see, we have 40 as our lowest number. It looks like it goes up to 80. So we'll go 4, 5, 6, 7, 8. So let's do the females first. So I see we have 43, 45, and 49. So that's 43. This part should be review. 43, 45, and 49 for those three values. There's a 51 and a 53. Remember to put them in order. So here's 51 and 53. All right, so we did the 40s, we did the 50s. Oh my gosh, I missed one. There's a 35. How lovely. So we'll do this. $35 and $38, no problem. So we have the 30s, we have the 40s, we have the 50s. There's 61 and 68. And so you should write these down on your notes as I go ahead. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Fantastic. So the females are done. So now let's do the male data. And the male data, you do it the same way, but remember the numbers should go from small to big as you go out of the stem plot. Okay, so if we put in the male data, we should put the numbers in from small to big. So it looks like there's no 30s for the males, no 40s either, so it looks like 50s. So we'll do 58, 59. So I do 59 first and then 58 because we want the numbers to go small to big as they go out. I think that's it for that. So for the 60s, we have 63 and 60. And that's it. So there we go. For the 70s, we have 72, 75, 73, 78. So I'm going to go 8, 5, 3, 2 for the 70s. Notice it's small to big, right to left. And for the 80s, I have 82. And I believe that's everything. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. So I got everything. So there's your two-sided stem plot. Sorry, it's a little bit messy. I want you to think now about why this might be useful data. You can see that we've represented all 9 females and all 9 males and put their values here. And do you notice anything about the data? Sorry, my camera's in the way a little bit. Do you notice anything about the data? Imagine, so here's what you can do with this. Imagine you're doing a focus group, and the way a focus group works is you get a bunch of people together and you hope that they're everyday people and that they're representative of the population, representing the demographics and various other things. And you show them, you're working for a political candidate, and so you show them a commercial that you're about to spend $100,000 on, or even $1 million on, or even $5 million on. So it's a really big, important commercial, and you want to show it to a focus group before you show it to the general public, before you spend all that money. And so say that you show the advertisement to a focus group, and then you ask all of the people to please write down how much they like the candidate after watching the advertisement. Okay, so you show the ad, vote for my candidate because he's great, vote for the other candidate because don't vote for the other candidate because they're terrible, blah, blah, blah. And then you ask them, on a scale of 0 to 100, please rate the favorability of the candidate. And let's say you get these scores back. Well, if I got this data back, I think we might have a problem because you can see that there's a really big split between the males and the females. Now, one thing I'd like to say that's really important is in statistics, we make generalizations. And please don't get upset if, we say something like, on average, the males like something more than the females. The point of this is because, as you can see, there's some females that liked the candidate more than males, in this example. So every person is an individual, yes. However, we can look at trends and we can look at things that correlate. And we can use that information to try to figure out why it's not working for females while it is working for males. So just things to keep in mind. There is a lot of money in focus groups, and you can get paid to participate them if you'd like. So hopefully you see that this two-sided stem plot is useful, and you can see that you can represent data for different groups and compare them. Okay, let's go back to the PowerPoint. We can so that's a stem plot. The next way of representing data is called a frequency distribution. And a frequency distribution is a table that shows how data can be partitioned among several categories or classes by listing the categories with the number of data points. So this helps us understand the nature of distribution. So it's basically the same thing as a stem plot, except instead of writing out every single individual, instead what we do is we have these various classes. So 25 to 27, we have 5 people. So here's our data over here, and you can see that they've scratched off the numbers as they've gone. So we have 5, in this data over here, we have 5 people that were between 25 and 27, 7 people between 22 and 24, 14 between 19 and 21, and so on. And you notice that we can add up the frequency column to get the total down here. So in the next video, I'll show you how to do this in the homework because it's a little bit annoying. So that's frequency table. You just have your classes, which are just ranges of values. Notice that each class needs to be the same size. So each of them go from 2 plus. Or if you're going from one class, if you're going from the lower bound from one to the next, notice that it goes up by 3 each time. So that's called the width right there. You can also do a relative frequency distribution, which is the exact same thing as this, except that instead of putting the numbers, we put the percentages. And so the right column should add up to 100% when you're done with that. So let's see if I have an example of that. I do not. Okay. I'll show you the example of that in the homework video. So relative frequency table, same thing as frequency, except instead of this, you would put the percentages. So let's actually build the relative frequency. Let's do it really fast. So I'm going to delete all of this. I'll just do the first 2 so you get the idea. So to make the frequency table, you just take 5 and you divide it by the total so that we can convert these into percentages. So you just do 5 divided by 40. So right here, that's going to be 12.5%, because 5 divided by 40 is, oh man, that's terrible. So that's going to be 12.5%. For the value of 5 because it's just 5 divided by the total. So now let's do the next one, 7 divided by 40. So you get 17.5% for the next one, and so on. You could do that for every single one of these. Okay, so that would be the relative frequency table with the percentages. So let's talk about how to build a frequency table as we move right ahead. First, you need to figure out the class width. And so you just need to figure out how many rows you want to have in your table. That's the number of classes. You take the maximum data value minus the minimum data value, and then you divide by the number of classes. The good news for you is you won't need to do this calculation in your homework because I believe on every single problem they tell you how many classes you have already, so we don't have to worry about it. Okay, this is an important slide. You will need this slide for the homework, so maybe put a star by this one in your notes. So the way you build a frequency table, the low class limit is the low end of the categories. The upper class limit is the upper end of the categories. I'll show you how to calculate the class boundaries because that's actually a little bit tricky. But basically, you just want to take your lower value and add the class width every time. And then you want to take your upper value and add the class width every time. That's the easiest way to do it. I'm also going to show you how to calculate the class midpoints. And as I've already mentioned, the width is the change from one class to the next. So I'm going to come back to this slide when we do the video on MyLabs Plus. And it's not that hard. It's just a bunch of things you have to remember. So I'll show you how to do that on the homework. Okay, so here we are. We're going to make a relative frequency distribution. And I'm actually going to show you how to do this in Microsoft Excel. I'm going to make a bigger video in the future about how to use Excel, but for now, we're going to use it. So we have the number of births at a major hospital were measured Monday through Sunday, so every day of the week. And so the question is, are babies more likely to be born on one day versus another day? And you can think of why that question might be important, because if you're the staff supervisor and you're scheduling everybody's hours, it might be helpful to know, is there a day on average where there are more babies being born? And if there is, consistently, then you might want to make the appropriate staffing consideration. But in any case, let's grab these values, and I'm going to open up the program Microsoft Excel. If you don't have access to this program, then you can do similar stuff with Google Sheets. So if you go to docs.google.com, and open up Google Sheets, you can access it for free. Well, sort of for free. Google uses your data, but you can do very similar things to Microsoft Excel. So this is actually maybe the best program people have ever created. So we're going to see how much you can do with Microsoft Excel, and it's a fantastic program. So let's put in the days of the week. I believe it started on Monday. So I'm just going to type them in. Monday, Tuesday, Wednesday, if I can spell. And you should be putting this in your notes as I go. So this will be a really quick introduction. So I'm going to start by just making the frequency table. So here we have our day. Let's do a frequency, and then we will do the relative frequency because they want us to make a relative frequency table. So notice I can just click and drag and drop to shrink the width and the length of these values. Okay, so I'm just going to type in the values right here. Easy enough. Okay, so there's our frequency table already done. And so here's what I'm going to show you. I'm just going to start simple. In Microsoft Excel, all of this is just data that I put in. So pretty simple. I just put in data. What I can do is make a formula. So in addition to just putting in a number, so like when I highlight the cell, you can see that there's the value right there. That's nice and helpful. However, where Excel starts to get really powerful is when you put in a formula. And the way you put in a formula is you have to type an equals sign. Okay, so the way you do a formula is you have to start by typing an equals sign, and that tells Microsoft Excel, hey, I'm about to put in a formula. So for example, you can put 5 plus 5, right? And notice that instead of leaving 5 plus 5 in the cell, it actually does the calculation. And so when I look at the cell, I see the number 10, but if I double click on the cell to edit it, you can see that what's actually stored there is the formula equals 5 plus 5. So the 10 is an illusion. Yes, it's the number 10, but what's actually stored there is the formula. By the way, I find that it's much easier to edit the formulas if you make a mistake by using this box up here rather than trying to do the formula inside the box. And the reason is because if you use the arrow keys to try to move around, it might grab cells in the spreadsheet, and then it just messes everything up, and you have to delete it all and start over anyway. So start by typing in an equals to type a formula, and then if you need to edit it, I recommend editing it up here. So that's nice. So now that we know that Excel is a giant calculator, what else can we do? Well, what we can do is use cells in our formula. And so watch this. If I type in equals A2, what it does is, remember the game Battleship where you would say A2 or B3 or D4 to try to sink the opponent's battleships? That's how this works. And so A, the letters are the columns, and the numbers are the rows. And so if I write equals A2, notice that it highlights the cell at A2 right there. And if I hit enter, it throws the word Monday there. Now, this isn't Monday. It's equals A2. But because the value at A2 is Monday, it just copies and pastes it right there. So that's nice. What we can also do is do numbers. And so I can do I can type equals 52 and it puts in the number 54. But let's say we need to, so why is this important? Because we need to calculate the relative frequency. And so we need to calculate all of these percentages. However, to calculate these percentages, there's a number we don't know, right? there's a number we don't know, and that number we don't know is the total. In order to calculate these percentages, I need to know how many babies were born in total, and that's what I need to calculate the percentages over here. So watch what I'm going to do. I'm going to type equals 54 plus 23 plus 36 plus 58 plus 40 plus 20 plus 46. Okay, double check that I got all the numbers correct. And so you can see that it's given me that the total is 277. So the total, in fact, why don't I put it down here? The total is 277. So that's really helpful. So you can see what I've done is I've added up all of the numbers. Here's another way I could have done that. All right, watch this. I could have done that this way. Equals B2 plus B3 plus B4 plus B5 plus B6 plus B7 plus B8. And one thing that's helpful is it gives a slightly different color for every cell. And notice that it gives me the exact same number. So you can either add up the numbers or you can add up the cells. And the better way to do it is with the cells. So either way, the total is 277. Now, here's where this is really cool. We want to calculate the relative frequency. And so what I'm going to do, I could type 54 over 277, and that's going to give me the frequency for Monday. However, it would be better to type B2 divided by 277. And so that's nice. You can see that it's put it as a decimal. And so what I'm going to do now is add on to my formula 100 times this amount, the entire amount. So I'll use parentheses for the order of operations. And so you can see that now it's a percentage, 19.49%. So please let me know if you have any questions. Oh, I can't make it any bigger. Please let me know if you have any questions about the, oh, there it is. Please let me know if you have any questions about the formula. 100 times B2 over 277. Boom, there's my percentage, 19.49. Now here's why Excel is awesome. What's stored here is the formula, not the number. And so watch what I can do. I can go up and use Control C to copy, and watch what happens if I hit Control V. Notice it gives me the percentage of this number. And the reason is because when I hit Control C and Control V, it didn't copy the number, it copied the formula. So notice it says B2 right there, and here it says B3. And I can copy that formula for every single one of these numbers. And so the way I did that was I just copied the formula again, Control V, so I had Control C to do that, and then Control V, Control V, Control V, Control V, Control V, and I have all of the rest of the percentages. So just like that, I made my relative frequency table. Once you get the hang of how to do this, you can do it very, very quickly. So that's how to make a frequency table. By the way, all of these percentages should add up to 100%, so let's see if they do. I'll do C2 plus C3 plus C4 plus C5 plus C6 plus C7 plus C8. I like using capital letters. You don't have to, but I like using capital letters. And you can see that it all adds up to 100%, so we did it correctly. In fact, if I copy the formula next to the total, notice it also gives 100%. All right, so that's your first introduction lesson to Excel and how to make a frequency table. Let's keep pushing ahead. Here's a histogram. A histogram is another way of representing data. It's basically the same thing as a frequency distribution, except that we use bars to represent the heights of the frequencies of everything. And so it's a visual way of making a frequency data. It's helpful if your data set is large. And what's nice about histograms is that you can see how the data is distributed. So you can see that this one is kind of a bell curve because we have most of the data in the middle with a little bit less on the other sides. Notice, by the way, I think there's a question in your homework about histograms, and the difference between a histogram and a bar graph, I guess, is that the histogram bars are touching unless you have no data. So the bars have to be touching for it to be a histogram unless you have no data. Now on this bar graph on the other side, you can see that it has a bell curve, but it has a really long right tail. Do you see that long right tail? So there's a few outliers up here, but most of the data is down here. And so you can see on the left, so this is about 9,000, a little bit more than 9,000 here. Here's about 8,500, but these bars over here have less than 1,000. So we call this a right skewed distribution. We'll talk more about that later. Relative frequency distribution, histogram is the same thing, except we have percentages on our left axis instead of the total numbers. So here you can see numbers 1, 2, 3, 4, 5, or 1,000, 2,000, 3,000. With the relative frequency, you have percentages. So these are both about 30%, these are both about 15%, and you can see this makes a nice bell curve. It doesn't always make a bell curve, right? So the normal distribution is maybe the most important distribution, but let's actually take now a look at some of the other distributions there are. So there are some other distributions. The first type of distribution, besides a nice normal bell curve, is a uniform distribution. So think about what the word uniform means. Why does a company make its employees wear uniforms? The reason is because they want their employees to kind of look the same and represent the brand. So when you hear the word uniform, think the sameness. Like the military has, all the soldiers have uniforms, and so they all sort of look the same. So that's uniform. So uniform distribution is where you don't have much variance, you don't have much standard deviation in your data. You're allowed to have some, right? But not very much. And so let's think of some examples of distributions that might be uniform. So if you do the age of students in a kindergarten class, well, they're all going to be roughly the same, at least within a year of each other. So that's pretty uniform compared to the ages in a high school, because that's across 4 years. So the kindergarten is going to be more uniform than the high school. Maybe the number of traffic tickets that the police give out is uniform if they give the same amount roughly out every day, so on and so on. So just think uniform, think sameness. We've already talked about the normal distribution. When you hear the word normal distribution, you should think bell curve. And as I said, there's the body in the middle with the two tails. Normal distributions are generally symmetric, meaning they're the same on either side. And in a perfect normal distribution, all of the central tendency statistics are the same, at least the mean, median, and the mode. And so they're equal. Okay, those are just two of the distributions. We're also going to study the binomial distribution in this class, and we're going to study the chi-squared distribution. And there's a lot of distributions. There's the geometric distribution, the exponential distribution, the hypergeometric distribution, the Poisson distribution, a lot of really good ones, but we'll only learn about a couple in this class. And if you'd like to learn about more distributions, then you should take more statistics classes. There's also alpha and beta distributions. There's a bunch. Okay, so this is a regular normal distribution right here with just the bell curve. We can also have it skewed right and skewed left. So if a normal distribution has a really long right tail, then we say that it's skewed right. And so skewed right means that most of the data is on the lower end of the bell curve. So you can see here's the majority of the data, and then there's a couple outliers out here on the right. And so that's your right skewed distribution. Also, the outliers are the higher numbers. So the higher numbers up here. So a classic example of a right skewed distribution is income in America. So we have the majority of people down here at about 30 to 40,000 GDP per capita dollars. And then you have this right tail with the data being skewed a little bit higher. And so that's an example of a right skewed distribution. A left skewed distribution, on the other hand, as you can imagine, is when the data is skewed left. And so the majority of people have a high value, and then you have a bunch of outliers over here that are making this left tail. An example that's easy to understand that I thought of for a left skewed distribution would be golf scores. So the majority of us are hitting really high values on the golf course, but there are a couple people who are really good, and so they have lower scores than everybody else, and so that's a left skewed distribution. I think it's funny that the object of golf is to play the least amount of golf. So there you go. So how can you tell the difference between a right tail and a left tail? Here's my easy way of doing it. This is literally how I remember it. So the way that I know if it's left skewed or right skewed is you can imagine if we were going sledding, right? And we were on our little sled. If the big hill is going to the left, then that means it's a left skewed distribution. That's a negative skew, and so most people have a high value with a couple people having a low value. On the other hand, if we're going sledding and the big hill is to the right, then that means it's a right skewed distribution, which is a positively skewed distribution. Most people have a lower value, and then there's a couple people who are outliers who have that upper value. And then most normal distributions are perfectly balanced. So it's most in the middle, a couple above over here, and a couple below over here. All right, so those are your distributions, normal distributions. Now, it is possible to tell how perfect of a bell curve a distribution has. And we're not going to do this very much in this class, but I think there's one question about it. So a normal quintile plot is a way to tell how normally something is distributed. And it looks like this value right here. So if the dots are on the line like this, then that means it's a normal distribution. And so data, I don't think I can draw on this, but if the data is a perfect bell curve, then your data dots will be falling on this line. If your dots do not fall, dots do not fall on the line, then you'll see some other kind of pattern like this one where it looks like a parabola on the line. And so on the left, here's the data that produced this quintile plot. And so you can see that the data is not a very good bell curve. It's a right skewed bell curve because of this right tail over here. So this is not a very perfect, normal, symmetrical distribution. So the way this thing is done is complicated, and we don't need to worry about it in this class. Okay, I'm almost done with the video. We have a couple different types of charts to look at, and then in the second video, I'll show you how to do some of the tricky problems on the homework. So there's a lot of different graphs we can do. The first is called a time series graph. That's where we have a line graph that represents the value of something over time. This is why you should invest in the stock market. Over time, the stock market goes up, and so if you're able to generate any extra savings, if you put them in the stock market over time, the stock market will work for you. However, there are some dips. The gray bars here are recessions or depressions, and so you can see here is the Great Depression right here in the 30s. Here was the Great Recession we had in 2008, and so you can see that although there are some downturns, the general trend is for things to go up if you diversify and if you get your money in the stock market. Over time, if you let it grow, it will help you. But I'm certainly not a financial advisor, so please take that with a grain of salt, but I think most people would agree with what I just said. Another kind of graph is called a dot plot. That's where it's basically a stem plot, except instead of putting in numbers, we just put a dot for every single person. So that's a dot plot. Same thing as a stem plot, except you just put the dots of each category. So you can see here they rolled the dice a bunch, and we have a bunch of different values for that. As I said, here's a bar graph. It shows frequency. Unlike a histogram, it does not, the bars don't touch. And the other thing about a bar graph is that it might be normative data. And so with the histogram, you were able to put the classes in order from smallest to biggest. With the bar graph, maybe it's more useful for normative data where you just have categories and you don't have a way to order them. This is a Pareto chart. Pareto charts are really useful in economics. The difference between a Pareto chart and a histogram or bar graph is that you always go from biggest to smallest. And so here you can see that our biggest bar we put first, then we put our second bar, and then our third bar, and each bar, notice it gets smaller and smaller as we go. And so that's a Pareto chart. You can also add in the cumulative frequency. So this isn't relative frequency, it's cumulative frequency. And so what that means is you have the percentages here, but you notice the line is always increasing. And so let's say that this first bar represents 25%, then, or actually let's see, 33%. So that first bar is 33%. and then the next bar is 27%, and so you add those together, and that gives you the second dot of 60%. So it's 33%, then we add on the second bar, so it jumps 27%, and so notice this line gets a little bit flatter every time with each increase, and that's because the amount we're adding each time is getting less and less. And so these show you the total amounts, and these show you the total of each category, and this shows you the total frequency, the cumulative frequency. So it starts growing big, and then it tapers off as the amount we add gets lower and lower. And notice that by the end, it's at 100% because we've added all of our data together. So that's a Pareto chart. Hopefully you know what a pie chart is. The pie chart should add up to 100%. One thing that you might not know about a pie chart is the correct way to do a pie chart is, like with the Pareto chart, is you should always start with your biggest chunk first, then do your second biggest chunk, and every chunk should get smaller and smaller. So that's actually the correct way to do a pie chart, is start with your biggest chunk, then the next smallest, next smallest, next smallest, next smallest. Notice if you're doing percentages, then at the end of the day, they should all add up to 100%. Next, we have a frequency polygon. It's similar to a histogram. So it's the same data as a histogram, except instead of doing bars, we just do dots and we connect them with lines. So this is the exact same data as a histogram, like this one or this one. Same exact thing, except instead of having the bars, like this, what you do instead is you just draw your line like that, and the line should hit the middle of the bars. That's the correct way to do it. And so the line I'm drawing, so the line I'm drawing, that's what we're talking about. So that line I'm drawing, that's what your frequency polygon looks like. So same data as the histogram, it's just you use a line instead of bars. The last type of graph that we're going to look at in this class is called an ogive. And an ogive is the same thing as a frequency polygon, except we do the cumulative instead of the histogram. So this represents the cumulative frequencies, similar to this line right here. So the cumulative frequencies as we go. So if we were to do the frequencies of this, so you might do it like this. So this bar has some data, so we'll put it right there. This bar is higher, so it should be steeper. This is the same amount, so that should have the same steepness as the previous line, roughly. This is the steepest one because it has the most data. And then we have quite a drop off, so it drops off a bit, then it drops off even more. Then in this category we have no data, so it should be flat. And then finally we have a little bit more data at the end, and so it should go up a little bit more at the end. So this is showing you the contribution of each bar as we go from category to category. All right, let's talk very quickly about my favorite part of statistics. And that is how to lie with statistics. Just kidding, that's not actually my favorite part of statistics. But this is actually a real book that I encourage you to buy. You can probably get it off Amazon. It's a book that's been around a long time. It's a really clever book called How to Lie with Statistics. We're going to see in this class how easy it is to mess with statistics. And, you know, there's that old joke that there's lies, damned lies, and statistics, right? So we've already looked at a little bit of two ways to lie with statistics. The first way is to have your bar graph not start at 0. So these two bar graphs represent the same data, okay? The interest rates from 2008 to 2012 for a company or for some bond or something. So they both represent the same data. However, here you can see that we started at 3.14%, and look how many decimals we go to make it look like there's this big increase that's happening. But in reality, if you start the graph at 0, like you should, it's increasing, but only very slightly. Only very slightly. So that's one way to misrepresent statistics with graphs, and people do it. Another way to mislead things is with pictograms. And so here's the idea here. You shouldn't use 2 or 3-dimensional graphs or images to represent one-dimensional data. So like, for example, here it's telling you how much milk you sold. And in the first year, 1997, you sold 10,000 cartons of milk. And in the second year, you sold 20,000 cartons of milk. And so that sounds great, but you're sitting there thinking, how can I get a bigger bonus? How can I show my boss how much more we sold? And so that I can, if you're the salesperson, for example, so that you can get a bigger bonus. And so, it is the way they justify this is if you look at the height of this, it is 10,000 tall, and the second one is 20,000 tall. So that shows you, it doubled. But the problem is you're also blowing up this dimension and doubling that one as well. And so the total effect of doing that is visually, it looks like you have 4 times as much, not twice as much. And so to the eye, it looks like, a 4 times increase instead of a 2 times increase. In fact, if I cut out this milk carton, you can see how it's only a fourth of the size of the big one. And if you do it in 3 dimensions, you can multiply something by 8 by doubling it. And so it's even a bigger miscommunication. So beware of pictograms and beware of bar graphs where the bar does not start at 0. That's just 2 of the ways that you can lie with statistics. There's many, many more, and we'll look at a few more in this class. So that covers everything you need to know for Chapter 2. Please let me know if you have any questions. I'm going to make one more video on how to do some of the trickier homework problems, and then we'll be good. So thanks for watching, everybody. I hope you made it to the end, and I hope you have a great day. Remember that you should aim to be done with all of your Chapter 2 homework by the end of next weekend, which ends on the 11th. All right, we'll see you later. Bye-bye.